can use what? Same thing, NaOET if you want, or you can use an LDA, or sodium hydroxide also is okay. Anyway, as long as it's made, I'll accept that. Then from here, you can alkylate it. So from here, let's put an R group on there. But let's say we wanted to make, we didn't want this part here. So in other words, we wanted this part, but not that part. Okay, so from here, what we could do is treat with H3O+. And what happens when we treat that with H3O+? Turns it into a...
1O with a methyl attached.
Into a...
A 1O methyl. All right.
Yeah, so that's going to get rid of the OET and make it into a acid. Yeah, so that makes it into an acid. So now note that what happens, this is a beta keto acid. And if we apply heat to this, okay, so this is a beta keto acid. If we heat this up, that's going to break this bond and pass that decarboxylation reaction. So that's the second way to break a carbon-carbon bond. So the first way to break a carbon-carbon bond that we talked about was ozanolysis. So this is the second way, this decarboxylation. So this loses CO2, so we'll put the minus CO2 here, and that's going to make this compound. Okay, so that's the second way to do this. The second possible way to do it.
Decarboxylation.
Decarboxylation. Yeah, so the minus CO2, this is the decarboxylation reaction.
Is there an oxide and stuff?
Which one? Giovanni?
The other side is on the top.
Heat.
Oh, heat. Oh my god, yeah.
Oh, yeah, heat. Delta for heat.
What are my guesses?
See, this is the one. Now, this is the symbol I use because this is the general reaction one for heat. Yeah, heat.
Yeah, I know what my guesses.
It's the OET and ONE and AEIOU and yeah, so that's another way you can do this. So remember that decarboxylation if you want to break a carbon-carbon bond. Yes, that's a good way to do it if you want to have a higher yield. Yeah, so anyway, from here, see, this is a beta keto. Let's see, if you have a beta keto, a beta diacid that also decarboxylates. When you look at that malonic ester and acetoacetic ester, those are two different ways to do that decarboxylation. Yeah, this is the acetoacetic ester. Yes, this compound is this one. Actually, let me go back. Let me find that slide because we talked about that in class. That was right here. That was this one. Yeah, so here's what it says. It said here that we can use the enolate to the nucleophilic substitution reaction to go from here to there. Okay, so that's similar to what we did there. But then the textbook said elimination competes with substitution, get poor yield. So the better way, according to the textbook, is use this malonic ester synthesis. So here's the malonic ester, which is this compound. And then the acetoacetic ester is this compound here. Okay, so it already has the OET on there already. So from here, this slide shows how we can go from here, the malonic ester. The Z is another ester group. If Z is a carbon, we get the acetoacetic ester. So anyway, we can go from here to there, the decarboxylation to form that compound. This is a way to alkylate an acid. This is a way to alkylate a ketone on the alpha position. So, like I said, those are important in biology. If you continue on, let me go back here. If you wanted, we talked about glycolysis, but if you want to look at, for example, this pyruvate to acetyl coenzyme, there's a decarboxylation reaction there. And then, let's see, I think in the Krebs cycle, let's see, is there a decarboxylation reaction in the Krebs cycle somewhere? Yeah, there's actually decarboxylation in this step here. That's step 4. Or step 5, there's a decarboxylation reaction.
Oh, yeah. That's right.
So anyway, I'll go back to that melanic ester one. See that melanic ester one. That was one on emails and emails. That was chapter 22. Okay, so maybe before you guys leave, we'll just summarize. Okay, so for me, whenever I see an aldehyde or ketone, the reactions I think of are the nucleophilic addition. Whenever I see an acid or an acid derivative, I think of nucleophilic acid substitution. And note that these two compounds have an alpha, so here's the alpha carbon here. So note that we can remove a proton from that alpha carbon, then that would be the aldol condensation or the nuclease condensation reaction. Or since we have the enolates, then we can also see, to me, the aldol condensation and nuclease condensation are similar, or applications for that reaction. So for me, instead of thinking of a brand new reaction, I think of note that here we're still removing that alpha carbon, either here or there, and then we can alkylate. But then the new part about these reactions is the decarboxylation step. Okay, so note that in the decarboxylation, here we have a beta diacid because we have our alpha and beta. So note that this acid group is 2 carbons away from that acid group, so that can undergo decarboxylation. Or we have this beta keto acid, same thing. So the ketone group is 2 carbons away, so we can decarboxylate that. So that's another structural feature that you can use now. And then earlier this semester, when we looked at those electrophilic aromatic substitution reactions, okay, so whenever you see a ring, okay, so think of electrophilic aromatic substitution reactions.
Are we going to do anything on forming rings from
Yeah, that was at Diels-Alder, we skipped it. I mean, there's other ways to form rings besides the Diels-Alder. For example, there was a problem in the textbook. It was, I think it was something like this. It was a long chain, and there was a ketone group there, and a ketone group there, and then you can actually form a ring from this by treating this with some like sodium OET.
oxygen?
What do you think happens there? So what happens is that, note that this is, and then from there, what can happen? Yeah. Yes, that's going to react here. That's another way to form a ring.
We're going to do like ring opening like oxide seams.
Oh yeah, so we talked about, that was earlier, we talked about the alcohols and ethers. So we know that the alcohols, we know how these react. we know that ethers in general are unreactive, so like you said, Jackie, the reactive ethers are the oxides. These are the reactants.
Are the the ether, whatever that thing is, ROR, is that, can that become reactive if you protonate it?
Yep. Yes, because you can do that to make an alcohol. So if you protonate that. Yeah, so now you have you can react it here. In the substitution reaction, that would be the image to do that. Because that's actually a way to, because in that Dolson synthesis, we did that ether synthesis from acetaminophen. We converted that to, we converted the alcohol. We converted an alcohol to an ether in that first step. And you can go backwards by doing what you just said there. Convert the ether back to alcohol.
What about esterification and trans-esterification?
Yeah, so that's actually, those are two examples of this nucleophilic acid substitution reaction. Yeah, because you have your instead of the acid, you have the ester group. Yeah, so I mean, for me, in some ways, there's just four reactions: addition, diffusion, substitution, and the substitution reaction with it. Yeah, so instead of looking at all the reactions, I don't know how many to look at. Just try to apply what you learned to the difference you should do. Okay, so on Thursday night, make sure you get a good night's sleep. You don't want to stay up all night.
As far as glycolysis goes, all those questions and comments on that, or the we do glycolysis on Monday. Will there be questions taken from that?
Yeah, it could be. Yeah, but if I ask you a question of glycolysis, it could be, for example, what type of reaction is that static? What type is it? Like, is it an oxidation reaction or substitution reaction? No, I'll give you the structure.
Oh, and then it doesn't say what it is.